Hello and welcome to the lecture number 8 of Physics 401A. In this lecture, we will discuss a very important theorem of classical mechanics, quantum mechanics, and in general field theory in physics. So it's a very important theorem for advanced physics. Okay, it is called Noethers Theorem. Noether's theorem was first derived or rather proved by German mathematician, female science mathematician Amy Noether. Okay, she proved it, as far as I remember, in the year of 1915, but finally could publish it in a journal uh, by 1918, so almost 3 years after the derivation or the proof. The theorem's real value can only be perceived when you will do field theory or quantum mechanics. Here it is a very interesting theorem. You will see a very elegant theorem, but the real importance can only be perceived when you will do those things like quantum field theory, even classical field theory, okay, and quantum mechanics, this type of thing. Okay. The formal statement of the theorem is that to every continuous symmetry, okay, there always exists a conservation principle, or that means more precisely there exists a constant or an integral of motion. Okay, so what is the meaning of continuous symmetry? The meaning of continuous symmetry is that a symmetry operation which can always be defined both in infinitesimal and in finite amount. Okay. So first we have to understand what a symmetry operation or symmetry transformation is in the current framework. Okay. For our case, it simply says that such transformations under which the basic equations of motion does not change their form are called the symmetry transformation. Okay. So under which the basic equations of motion does not, or rather do not change their form. Okay. In the framework of Lagrangian mechanics, we have to allow, therefore, only certain transformation of Lagrangians so that the basic equation of motion do not change. Okay. So basically we are propagating the symmetry property from the basic equations of motion to the Lagrangian, and now we are reconstituting the same statement of the Noether's theorem by saying that if the Lagrangian of a system is invariant under a transformation, or otherwise, in an alternative way, if we say that if we talk about or if we define a symmetry transformation of the Lagrangian of a system, then if the symmetry transformation is a continuous symmetry transformation, that means we define an infinitesimal symmetry operation for this transformation, then there will be a conserved quantity of or constant of motion corresponding to that symmetry operation. That's it. Now we know that under any arbitrary additive transformation or additive shifts, Lagrangian is not always giving the same equations of motion. The only condition when the Lagrangian, as we saw in the previous lecture, that the only condition under which the Lagrangian gives the same equations of motion is when the Lagrangian is only shifted by ddt of a function of the generalized coordinates q and t. Then only we showed that finally the corresponding action does not change. The stationary action path always remains the stationary action path, or the path does not basically change, and if the path or the trajectory does not change, that means the equations of motion will not change. And also as an intermediate conclusion, you can also see that the form of the Euler-Lagrange equation will also not change, right? So for that, you have to know that the difference between the new Lagrangian and the old Lagrangian will simply be a ddt of f, where f is a function of q and t only. Okay. Now for infinitesimal transformation, we write that delta L infinitesimal is equal to ddt of epsilon f, where f is the general functional form and epsilon I have multiplied to make it as an infinitesimal change, where epsilon is an arbitrary smallness parameter of first order. Now that was the only condition when the Lagrangian is transformed, is undergoing a symmetric additive transformation. Okay, so there are two things. One is symmetric because it doesn't change the Lagrangians, it does not change the action. The Lagrangian of course changes, but it does not change the action. Okay, and also it is an additive transformation. That means it is not a multiplicative type of transformation, this is an additive. So L prime should be L plus something. Okay, now we are considering, if we are now talking about L as a function of q, q dot and t, then any arbitrary change, okay, of Lagrangian, of course by an infinitesimal amount, and that's why we are talking about the change up to first order only. So any arbitrary transformation of Lagrangian, which we define simply by this symbol delta L, will then be equal to summation over I del L del Qy delta Qy, where I of course running from 1 to n, where n is the number of degrees of freedom or the number of generalized coordinates of the system, plus summation over I del L del Qy dot delta Qy dot plus del L del T times delta T. Now we are talking about, in this context, for the first as a first step, the Noethers theorem of the first type. That means we will be limiting ourselves to the such transformations where either delta L delta T is equal to 0. Okay, that means the Lagrangian does not explicitly contain time. There is a time dependence, but it's an implicit dependence through q and q dot. Or another thing, and that is the most prominent thing actually in this case, that delta T is equal to 0. That means the time explicitly does not change here. Okay, so we will change the Lagrangian in such a way that the explicit change of time is not meant. So the time, we can do also, we can do that, right? In that sense, both the generalized coordinates and generalized velocities, either they will suffer virtual displacements or they will suffer simply a constant displacement. Okay, constant displacement is actually a trivial case. Okay, and under this case, you can simply write then delta L infinitesimal is equal to summation over I ddt of del L del Qy dot times delta Qy. Why? Because del L del Qy, this term by Euler-Lagrange equation, is simply this. Now you can see that this is, here we are perturbing the Lagrangian, or rather we are expressing the perturbation of the Lagrangian up to first order, but with respect to the real trajectory on which Euler-Lagrange equation is valid. That's why for these parts we can easily use the Euler-Lagrange equation. Okay. Plus there will be another term, summation over I del L del Qy dot times, now delta of Qy dot I can write for our present case as ddt of delta Qy, where delta and ddt, they commute each other. Okay, because ddt corresponds to the total time evolution on a real trajectory, and delta corresponds to the changes or the perturbations where the delta t is zero basically. Okay, so either some constant transformations or some more generally some virtual displacements. So that's why delta and ddt, they commute each other. If they commute each other, then you can write simply this form. Now if we have a look at the total expression over here, okay, let me just do that. Yeah, the total expression over here, then you can say that this is nothing but summation over I ddt of del L del Qy dot times delta Qy. Okay. Now again, if we assume that if our potential, if we are talking about let's say the conservative system for which the potential function is independent of the velocity, then you can write your pk or the conjugate momentum as equal to del L del qk dot, right? Then if we use that definition, then we simply can write this delta L infinitesimal is equal to summation over I ddt of pi delta qy. That's exactly what it is written over here, this. Okay. And you can understand this was an arbitrary infinitesimal change of Lagrangian, of course under the restriction that delta t is 0 or delta L by delta t is equal to 0. Actually delta L by delta t is equal to 0 can actually pose the problem. So let us take mostly this case only for this purpose, that delta t is 0. So we will be only considering such transformations where t is not changing. It is called the Noethers theorem of first type or first kind. Okay, so the simpler form. Okay, now for those cases you can say that this is an arbitrary change, and if the arbitrary change is giving a symmetric transformation of the Lagrangian, then only our purpose is served, right? And under that condition, and this is only possible when this arbitrary change is equal to ddt of epsilon f, where f is a function of q and t. Okay. Now epsilon in general, this is the smallness parameter, but it may or may not be a function of time. Now here again, in this context, we are only talking about the epsilon, which is not a function of time, but you can always keep this epsilon as a function of time as well. But the only thing is that here on one side, if you are claiming that the changes are time independent, and here if you are saying that my changes are time dependent, then sometimes this can cause some confusion or something. But in general you can say that there is no how to say that there is no any control, no any problem in this. Okay, so what I am just trying to say is that this epsilon, if it is constant, it will just come out of this, or if it is just not constant, it should be in. Let us for instance put it inside ddt, no problem in this. Then this will be equal to this, okay, under the condition that the Lagrangian is perturbed, so that finally it undergoes a symmetric transformation. And that simply says that ddt of summation over pi delta qy minus epsilon of f, the whole thing, is equal to 0. So summation over pi delta qy minus epsilon f will be a constant of motion. Okay, so finally you see that we started by saying that we are assuming that our Lagrangian is undergoing some symmetric transformation, additive type of symmetric transformation, and finally we showed that corresponding to that transformation we finally have a constant of motion. So this part is this part is given by the pi's and delta qy's. Okay, that means the variables of the Lagrangian, and this part is given by the epsilon times f, where this function can only be determined if we directly calculate how much the total functional Lagrangian is changed, and if the total change can at all be expressed as a df dt or not, where f is a function of q and t, right? If you can prove that, then you will have the form of f. Then by substituting this, the form of f into this expression, finally you can calculate the constant of motion. Okay. Now remember, here we always have talked about continuous symmetry transformation. That's why we are talking about infinitesimal changes, first order perturbation, and Taylor expansion type of thing. Now note that for discrete symmetry transformation, this theorem cannot be valid in general. Okay. My question, or rather I invite you to think on it, and why. Basically, mathematically, if you just see this derivation, at which step this may cause a problem. Okay, so just think and try to answer me later. Okay, now we discuss some application of Noethers theorem. Very easy but very interesting as well. First is the conservation of linear momentum. I promised you in the very first lecture or in the second lecture that we will come into this conservation principles of classical mechanics, which we showed previously using Newton's law and those things, that we again revisit these conservations from a different point of view, and that will be the point of view of symmetry. Now this is the occasion where we will talk about the symmetry and the corresponding conservation. Now let us consider the Lagrangian of a point particle of mass m to be equal to half m summation over I xi dot square minus v of x. Okay, this is simply a system of particles. So basically, it's just a single particle, but having a number of degrees of freedom. Of course, the I gives the summation over the number of degrees of freedom. So in the beginning, if we assume that the particle is free, that means no force is there. So then we know that dv dx is 0, or minus dv dx is 0. So v is a constant. So let us define this constant as minus of c. Then the Lagrangian simply becomes half m summation over I xi dot square plus c. Now if we investigate the effect of infinitesimal translation in space on the Lagrangian, then we will see what will be the corresponding conserved quantity using Noethers theorem. Now we know that infinitesimal translation is of course an infinitesimal additive type of transformation. Now whether it is a symmetric transformation or not, we don't still know. Now first, to see how to mathematize this transformation. So the transformation simply says that for every xi, it will simply be xi prime after transformation, which will be equal to the old xi plus ai. So ai is the ith component, okay, of the small infinitesimal translational vector a. Okay. Now if this is changed, xi is changed by a constant amount, then of course you can understand that xi dot will not change because ai is constant. So xi dot simply will be xi prime dot, right? So there will be no change in the velocity components. And delta xi, which is nothing but xi prime minus xi, will be ai, and delta xi dot will be 0, because in the old and new velocities, there will be velocity components, there will be no change. So with the change in xi only, the new Lagrangian will then be L prime is equal to half m summation over I xi prime dot square plus c. So c will not change, this is the constant. Okay, so only the xi has been changed to xi prime, and xi dot to xi prime dot. Now you know xi prime dot and xi dot, they are the same. So finally this is equal to half m summation over I xi dot square plus c, which is the old Lagrangian. So the old Lagrangian and the new Lagrangian, they are exactly the same. So delta L or L prime minus L is 0. So if we say that ddt of epsilon f is delta L, then this is exactly 0. So this is basically nothing but a case of trivial transformation of Lagrangian. The Lagrangian basically stays the same. And that says that epsilon times f is a constant function, let's say c star. Okay. Then, as we said that if you can remember this will be the constant of motion summation over I pi delta qy minus ef. Now if ef is a constant, then actually by saying that actually this is equivalent to say summation over I pi delta qy itself is a constant, and that's exactly we used here. Okay. Now this is nothing but the scalar product of p dot a. Now this is true. So p dot a is a constant. Now a is where a is a constant vector and arbitrarily chosen, then you can actually show that p dot a constant simply says p is also equal to constant, right? So I mean, many of you can be confused by saying that p dot a simply says that the angle between those two vectors are constant. But how to say that? So if a is a constant vector, then I mean we can know that p's orientation will be constant. But how to know that p's magnitude is constant? So one possibility is, of course, to say that a is arbitrarily chosen. So every time by choosing such particular a, so that only one component is non-zero, then you can easily say that show that every component of p is zero, p is constant. That is one possibility. Okay, let's say a is like a vector is equal to axi plus 0j plus 0k, then you can easily show that px is constant, and in the same way you can show py and pz are constants. Another very easy way is that you can write a, if you can, so a can be arbitrarily chosen, so you can write a is equal to some very smallest parameter epsilon times p itself. So then p dot epsilon p is epsilon times mod p square, and epsilon is non-zero and also it's constant for a specific choice. Then you can say that p square is constant, so mod p is also constant. Okay. So all this, I mean, this is very easy to understand. So the conclusion is p vectorially p will be conserved. So p is a constant vector, and which is nothing but the linear momentum vector. So we can see that for a free particle, the linear momentum vector is a conserved quantity. So here basically the conservation comes due to the symmetry of Lagrangian under infinitesimal translation in space coordinate, right? Now what happens if Vx is not a constant, that means there is a non-zero force, then you will have half summation, the new Lagrangian L prime will simply be half m summation over I. So xi prime dot and xi dot, they are the same, so I simply write that as xi dot square plus the v will now be v of x prime, and which will be v of x plus a. And this is, so basically then you already expand this as v of x plus dv dx times a, and so this is basically a minus sign, okay. And finally you can write that v of x you can get absorbed with this term to get old Lagrangian, plus you will have minus dv dx time dot a. Okay, so minus dv dx vectorial is nothing but the gradient of v, okay. And this is equal to L plus f dot a. Now in general it is not expressible as a total time derivative, that's why your p is not conserved. Now let's say if f is constant, then it will be a constant. So then your del ddt of epsilon f itself is a constant. So epsilon f will simply be this constant time t. So it will be a time dependent function. Okay. Try to think what happens. Whether we also can say that for this p is not conserved or p is conserved. That means f is non-zero but is a constant. Okay. Think about that. Of course, as you can know that, as you all know that for a system with constant force, the momentum is no longer conserved, right? Okay. Now coming to the second type of conservation principle, that is the conservation of angular momentum, and for that we take, for simplicity, the case of the motion of a particle under a central force, where the f is only a function of magnitude of r and its corresponding potential is also central, so it will be v of r. Now since the motion is in a plane, we use 2D plane polar coordinates, whence the Lagrangian becomes simply it is equal to, we have previously seen that, half m r dot square plus r square theta dot square minus v of r. Now how to incorporate in such a way, in such a formulation, the effect of an infinitesimal rotation? That simply says that if your like the plane of, you have 2D polar coordinate system. Now if you just rotate the polar coordinate system by an angle, let's say small epsilon, then this is equivalent to saying that the r vector, that the r, okay, the distance from the origin to any arbitrary point, okay, will not change, but its theta coordinate will change. Okay, so then the r will simply be r prime, which is equal to r, but the theta will now be transformed into theta prime, which simply be equal to theta plus epsilon. Epsilon is the new amount of infinitesimal rotation. R dot will not change, it will be r, so r dot, if it is now written as r prime dot, it will simply be equal to r dot as well, and the same thing will be for theta dot. So the dots are not changing because epsilon is a constant amount. Okay. Now if we write the new Lagrangian L prime, we can simply say that half m r prime dot square plus r prime square theta prime dot square minus v of r prime, right? Now here you can see that the theta is not appearing explicitly in the form of Lagrangian because it was cyclic coordinate, as you all know, and so finally all these things are getting unchanged to give us back the old Lagrangian. So again, this old Lagrangian and the new Lagrangian, they're exactly the same. So this epsilon f is again constant. Okay. And what about this summation over del L del Qy dot delta Qy? It will now have two contributions. Del L del R dot delta R, which is 0 because delta does not change, and it will have del L del theta dot delta theta, which is nothing but PL theta, that means the angular momentum component, or which is the conjugate momentum with respect to the theta coordinate. Okay, so it is the magnitude of angular momentum actually times epsilon. So epsilon is the delta theta. Okay, and again epsilon is constant and arbitrary, so we can have PL theta is constant. So the component of the angular momentum along the axis of rotation is conserved, and as you all know that if you calculate directly just by just by knowing the definition of central force, that if you try to calculate, or rather how to say, if you know how to write the velocity vector in this case of 2D polar coordinates, then if you just write r cross mv, you will see that this is exactly, the angular momentum vector is only directed along the perpendicular of the plane of motion. That means by saying, that means the saying the component of angular momentum along the axis of rotation, and by saying that the total angular momentum is the same thing. So if the component of the angular momentum along the axis of rotation is conserved, then we can say that the total angular momentum is also conserved. Okay, now so the here we can show that the magnitude is a conserved quantity, and its direction is also conserved because it is always perpendicular to a to the plane of motion. Okay, and the plane of motion basically does not change with time. Okay, so that is the conservation of angular momentum, which comes as a consequence of infinitesimal rotational symmetry of Lagrangian. That's very important. Huh? So you now have shown in these two examples that two type of infinitesimal symmetry transformations of Lagrangian gives us two very important fundamental conservation principles. Now you all know there is a third conservation principle, very usual, which is the conservation of energy, and some of you of course know as an information that it comes from the homogeneity it's the how to say that homogeneity of time, or that means the symmetric transformation of Lagrangian in time, under time translation. Okay, so how to do that? This is not very evident or immediate from this type of formulation of Noethers theorem of first kind. For that, I will give you a more generalized proof or derivation of Noethers theorem. Okay, so my question to you to think: can you prove this type of conservation principle of angular momentum for a rotation of a Cartesian system, where the direction of the rotation is given by an arbitrary vector n, which is equal to alpha x cap plus beta y cap plus gamma z cap. N is a unit vector basically. Okay. So they are the direction cosines. So think about this and let me know what you have thought. So thank you very much. Okay, here I am ending this lecture.